Hello everyone, my name is Yuchen Yang. I'm a PhD student in CPS Virginia Tech. Today I will give a brief introduction on GaN Based MHz PFC with Coupled Inductor. This figure shows the circuit topology of our two-phase interleaved totem pole PFC converter. L1 and L2 are two inductors for each phase. Traditionally, these are two independent inductors, but here we will build these two inductors in one magnetic core and make them coupled with each other. This figure is a demonstration of the coupled inductor structure. The arrow shows the current flow direction of the two inductors. We can see that L1 and L2 are negative coupled. The blue dashed line shows the mutual flux, and the green dashed line shows the leakage flux. Here shows the typical current waveforms of coupled inductor when duty cycle is smaller than 0.5. It can be seen that during one switching period, the current waveform has different slopes, which means that it has 4 equivalent inductance. Similarly, this figure shows the waveforms when duty cycle is larger than 0.5. After coupling, this equivalent inductance will change the circuit performance. The first benefit of the coupled inductor is that it can reduce the switching frequency. This figure shows the input voltage waveform during half-line cycle. First, let's look at the non-coupled case. For the traditional non-coupled inductor, the inductance is a constant value. The bottom figure shows the switching frequency variance during half-line cycle. Because the converter is running at critical mode, the switching frequency will change with input voltage. Then the coupled inductor is applied. First, the coupling coefficient is -0.5. It can be seen that the steady-state inductance will change with input voltage. When duty cycle is smaller than 0.5, the steady-state inductance is equal to Leq1. When duty cycle is larger than 0.5, the steady-state inductance is equal to Leq3. After coupling, this steady-state inductance is larger. As a result, the switching frequency is reduced. We can sweep the coupling coefficient to -0.8. It is very clear that coupling can help reducing switching frequency. Another benefit of coupled inductor is that it can help achieve zero voltage switching. For the non-coupled case, during resonant period, the resonant amplitude is 2 times VO minus Vin. VDS cannot resonate to zero when input voltage is larger than half of output voltage. Thus, ZVS cannot be achieved. After coupling, the resonant amplitude is increased. Therefore, VDS has the ability to resonate to zero and achieve self-switching. Then the balance technique is applied to this coupled inductor structure to minimize common mode noise. In order to do that, 2 inductors L3 and L4 are added. So we have 4 inductors coupling in a single magnetic core. This figure shows the CM noise model of this converter. If the balance condition is achieved, the CM noise will be reduced. Here is the experiment result. It shows that with balance technique, the CM noise can be reduced by 15 dB. We are able to integrate these 4 inductors into 6-layer PCB board. This figure shows the cross-section view of the inductor. Here we interleave the winding of L1 and L2 to reduce the winding loss. In addition, we can cut some winding to avoid fringing flux. This is the FEA simulation result and the loss breakdown. It can be seen that the PCB winding inductor has the same loss as the traditional lead-wire inductor. This is one state-of-the-art PFC inductor. It is toward the core with traditional winding. This is our proposed coupled inductor. It has 4 inductors integrated into 6-layer PCB board. Therefore, this inductor can be integrated into the circuit motherboard. With this integrated PCB winding inductor, the converter can achieve higher power density and lower CM noise. Furthermore, it can avoid labor-intensive procedure and achieve automatically production. That's all my video nugget. Thank you for watching.